In 2019, humanity photographed a black hole for the first time. Millions saw the glowing ring. Almost nobody noticed the strangest part. The picture shows everything except the black hole itself. Everything we can ever see stops at the edge. This is the story of what lies past that edge, and why the answer may rewrite physics. A black hole begins as a star, one at least 20 times heavier than our sun. For millions of years, the star burns, and the outward push of its own light holds up the crushing weight of its layers. Then the fuel runs out, the push stops, and gravity, patient for all those millions of years, finally wins. The core collapses in less than a second while the outer layers detonate as a supernova, briefly outshining an entire galaxy. What happens next depends on the weight of the collapsing core. If the core weighs less than about 3 suns, the collapse stops. It becomes a neutron star, a sphere the size of a city, so dense that a single teaspoon of its matter weighs about 4 billion tons. But past that limit, no force known to physics can stop the fall. The core keeps collapsing through the neutron star stage, through every form of matter we understand, until it vanishes behind a boundary of its own making. A black hole is born. The recipe is brutally simple. Compress anything enough, and it becomes a black hole. Squeeze the sun into a ball 6 kilometers wide, and it turns into one. Squeeze the Earth to the size of a marble. Same result. The universe just happens to use dying giant stars, because only their gravity can do the squeezing. The boundary is called the event horizon, and it is the most misunderstood place in space. It is not a surface. There is no wall, no membrane, nothing to touch. It is simply the line where escape would require moving faster than light. And nothing moves faster than light. The horizon does something else remarkable. It freezes time, at least from the outside. Watch a clock fall toward a black hole, and it ticks slower and slower, its image dimming and reddening, until it appears to stop entirely at the edge. In a very real sense, the outside universe never sees anything finish falling in. But the falling clock disagrees. From its own point of view, nothing special happens at the horizon. It crosses the line in a fraction of a second and keeps going. Two observers, two completely different stories, and according to relativity, both are correct. So what does the clock find inside? Einstein's equations give one answer, and they give it with total confidence. Everything that crosses the horizon falls inward, and space itself falls with it. At the center, all of it, the dead star, the gas, the clock, is crushed into a single point, the singularity. At the singularity, the math says density becomes infinite. The curvature of space becomes infinite. Time ends. And this is exactly where physicists stop trusting the math. In physics, an infinity is rarely a discovery. It is usually a confession, the theory admitting it has been pushed past its limits. General relativity rules the world of the very large. Stars, galaxies, gravity itself. Quantum mechanics rules the world of the very small. Atoms, particles, fields. Inside a black hole, the very large is compressed into the very small. And our two best theories of reality are forced into the same room. They contradict each other. The contradiction has a name, and it started with a rule. Quantum mechanics insists that information can never be destroyed. Burn a book, and, in principle, the ash and smoke still encode every word. The universe is not allowed to forget. Then, in 1974, Stephen Hawking found something nobody expected. Black holes are not perfectly black. Thanks to quantum effects at the horizon, they glow faintly and slowly evaporate. Given enough time, unimaginably longer than the current age of the universe, a black hole shrinks and disappears. And there is the paradox. If a black hole swallows a library and then evaporates in a featureless radiation, where did the information go? Hawking's own calculations said, it's simply gone. Quantum mechanics says, impossible. That argument consumed theoretical physics for 50 years, and it is still not fully settled. Which brings us to the real answer to our question. What is inside a black hole? Physics currently offers several serious candidates, each one stranger than anything science fiction has dared. Option 1. There's no inside. String theory suggests black holes may be fuzzballs, tangled balls of fundamental strings with no interior at all. What looks like an event horizon is actually a surface, and the information never falls in because there's no in. Option 2. The firewall. Some calculations suggest quantum effects turn the horizon into a wall of blazing energy that incinerates anything that touches it. Elegant for the math, catastrophic for Einstein, whose theory insists the horizon must be an unremarkable place. Option 3. The bounce. In loop quantum gravity, space itself comes in indivisible units, and collapse stops at the smallest possible scale. The star never crushes to a point. It rebounds in ultra-slow motion, a Planck star that might one day explode back out. No singularity, no ending, just an unimaginably long pause. Option 4 is the strangest, and it is currently the most influential. The holographic principle says all the information about a black hole's interior is stored on its two-dimensional horizon, the way a hologram stores a 3D image on a flat film. Followed to its conclusion, the interior may be a kind of projection, and possibly so is everything else. While theorists argue, observers keep gathering evidence. We now know a black hole of 4 million suns, Sagittarius, a star, sits at the center of our own galaxy. We photographed it in 2022. The giant in galaxy M87 weighs 6.5 billion suns. And every image so far matches Einstein's predictions, at least outside the horizon. Since 2015, we can also hear them. When black holes collide, they shake the fabric of space, and detectors on Earth record the ringing. That final ring is a fingerprint of the horizon itself. If black holes have firewalls, fuzz, or echoes, future detectors have a real chance of catching it. So what is actually inside a black hole? Here's the honest answer. We don't know. Not because the question is silly, but because it is exactly where our knowledge of reality currently ends. Whatever sits behind the horizon requires physics humanity has not discovered yet. That is what makes black holes precious. They're not just cosmic monsters. Every one of them is a locked box containing the next revolution in physics, the successor to Einstein, waiting to be opened. If you could get one answer from inside the horizon, what would you ask? Tell me in the comments.